So section 15.3, double integrals in polar coordinates. In the near future, I will be presenting this a different way. So I'll be presenting how to integrate using a change of coordinates in a more general way. And then I will further introduce integration by some sort of change of variable in an even more general fashion, first it will be involving determinants, and then it will be involving these quantities called differential forms and pullbacks, and they'll give sort of a very general sort of concept of why these formulas work. And it'll be just sort of falling out of algebra. The geometry of the algebra as determined by the geometry of space. Okay, so let us start section 15.3, double integrals in polar coordinates. So first, let me recall polar coordinates. So rather than having the x-axis and y-axis and looking at some ordered pair, we will then instead look at, boy, it's slow today, some polar axis and measure the angle from that polar axis and the distance, and then relating that point with this ordered pair. And so instead of having an ordered pair as determined by, well, the distance and the distance of the y-axis, I will look at the distance to the pole and the angle between the polar axis and this line as determined by the point. So suppose I have some rectangular coordinates, x and y. I can relate it to polar coordinates as follows. Well, x, I can let it be r cosine theta, and y to be r sine theta. Then, well, I can relate polar coordinates back to rectangular coordinates as follows. Well, if I just square each of these, x squared plus r squared, cosine squared plus r squared, sine squared, factoring out the r squared, I get so cosine squared plus sine squared, which is 1. Therefore, my relationship is that r squared is x squared plus y squared. Next, I can just divide these two quantities. So y equals r sine theta divided by x cancel. So I just get sine over cosine, which is tangent theta, is equal to y over x. So I can, given x and y, I can determine r and theta. Now there's a little bit of arbitrariness here. For one, I can take either the positive or negative square root. And for theta, well, maybe I could wrap around the pole several times and get back to the same point. So there's a little bit of arbitrariness here, but you know, that's the arbitrariness we have to live with when we're talking about polar coordinates. Okay, so suppose I have the double integral over a region described in rectangular coordinates, and I want to integrate some function in rectangular coordinates. That's the same as finding the double integral, where I have redescribed the region in polar coordinates, and I'm now integrating over r times the function written in polar coordinates. So basically the idea is that when I integrate, I have to multiply by a factor of r when I change to polar coordinates. Okay, so let's do, oh, I actually drew something. Problems number 7 through 14 on page 1054. Evaluate the given integral by changing to polar coordinates. So problem number 10. I have the double integral of y squared over x squared plus y squared, where r is a region that lies between two circles. So I have the region here that lies between two circles. X squared plus y squared equals a squared, and x squared plus y squared equals b squared, where a is between 0 and b. And so it's this region R, which is the region, it's this little annulus between these two circles. Okay, so now I want to transform it into polar coordinates. Okay, well, what you notice here is that x squared plus y squared equals r squared. That corresponds to r squared equaling a squared. Okay. Now, let's just assume that a is greater than 0. And so this just says that r is equal to a. So that's this region here can be described by, well, this boundary here can be described by this line. Notice that here we can say, well, we're only going around the circle once, so my angle only goes around the circle once, and so we just go from 0 to 2 pi. So my angle is just going from 0 to 2 pi. Well, I can do the same thing for this outer one. I can just say, well, that x squared plus y squared equaling b squared is the same as saying that r squared is b squared. Since x squared plus y squared is just r squared. And assuming that b here is greater than 0, I can say let r equal b. Again, there's some arbitrariness. I could let r equal negative b and all that. But to make my life easy, I'll just let it equal positive. And so this outside, these outside two lines correspond to these. And everything inside, since we're now sweeping around this whole region, same as sweeping the angle theta from 0 to 2 pi if I only go one time around the circle. And so this rectangle is the same as this annulus. So it turns out that integrating over this is not so easy, but integrating over this guy, oh, that's really easy. So changing from this region to this region makes my life easier. Similarly, the function that we're integrating y squared over x squared plus y squared. This will become a little bit easier. So when I switch over to polar coordinate, so y squared over x squared plus y squared. Well, let's see. I have y, which is r sine theta. So r sine theta, I'm going to be squaring that over x squared plus y squared, which is just r squared. So this is just equal to sine squared theta. So I can rewrite this from rectangular coordinates into polar coordinates. That's not so bad. Okay, so let's try to do this problem. Okay, so I want to integrate over my region R, y squared over y squared over x squared plus y squared. So this is equal to the integral. Well, let's do dr d theta. So let's go from 0 to 2 pi. So I'm just going to go 0 to 2 pi here, and from a to b in R. Of, well, rewriting this in polar coordinates, it's just sine squared theta times, well, if you recall, when I integrate in polar coordinates, I have to write it as r dr d theta. So just remember that dA becomes r dr d theta. Okay. So this is equal to, well, let's integrate. Let's integrate with respect to r. So integral from 0 to 2 pi of 1/2 r squared sine theta squared between r equaling a, r equaling b. So this is equal to integral from 0 to 2 pi of 1/2 b squared sine squared theta minus 1/2 a squared sine squared theta. So let me just factor out the 1/2 theta squared. And so let me integrate this. Well, I know that sine squared is one-half 1 minus cosine 2 theta. So let me use that fact. So this is equal to integral 0 to 2 pi of 1/4 b squared minus a squared of 1 minus cosine 2 theta. Okay, so this is equal to, let's integrate this. So this should be pretty easy to integrate. So this is just 1/4 b squared minus a squared theta. Integral of 1 is just theta. Minus integral of cosine 2 theta is 1/2 sine 2 theta between 0 and 2 pi. Okay, so I'm actually almost done, so let's just pull this down. Just probably only need like 1 or 2 more lines. Yeah, let's go for 2 lines. So this is equal to, plug in 2 pi, so this is 1/4 pi squared, b squared minus a squared. Plug it in 2 pi, you get 2 pi. Sine of 4 pi is 0. Plug in 0, that's 0. Sine is 0, 0. And so I get pi over 2 b squared minus a squared. And that is your answer. Okay. Let's do problems 15 through 18. Use a double integral to find the area of the region. So in calculus 1 or 2, calculus 2, in calculus 2, you did problems of the same sort. You just happen to use one integral rather than a double integral. You just used a single integral. We'll do the same sort of problem, but now doing it as a double integral. So you can sort of see where some of those, they gave you some formulas that were semi-arbitrary to figure out these areas. But now we're going to do it a little bit more generally, then we're going to redo it again, a little bit more generally, then redo it again in its full generality. Okay, so region bounded, so the region enclosed, so problem 16, the region enclosed by both of the cardioids, 1 plus cosine theta. So 1 plus cosine theta, again, a cardioid looks something like this. So it goes like this. And 1 minus cosine theta. So it goes, starts here, goes like that, like this. So again, they look basically like hearts. So both of them. And so to enclose both of them, well, it's going to be in between these two. So somehow I want to be to look at this region here, where I've enclosed both of these. Okay. So it's going to be, well, so let's find the area. So let's go from 0 to pi over 2. So this first region. And if I do that, well, let's see. So this will be, I'll start out here from the angle here. Well, so the angle here will be 0 to pi over 2, but this, here, yeah, I can sort of draw that. This length here, this r here, will go from 1 minus cosine of theta to 0. And this is r. And then I'm just integrating 1. So this is 1 r dr d theta. Plus, now let's go the other route. Let's go from pi over 2 to pi. Question: how do you pick the bounds of the integral? Yes, so that's what I'm doing. So here's my region. So this is, so let's draw this. So this here, I've drawn this is r equal 1 minus cosine theta. And this is between the angle theta equaling 0 to theta over 2. So this, I'm going to find this area. So the thing on the outside, actually, well, let's actually do where it looks like. So it looks like an R. So the length R here goes from 0 for that region. Now let's do the other region. Now this, on this side of that region, well, the angle starts here. So I've started, notice at 0, I'm over here. And then I go to pi over 2, I'm over here. Now from pi over 2 to pi is this region. So this is, I'm starting out at theta equaling pi over 2, ending at theta equaling pi. And this curve here is 1 plus cosine, right? 1 plus cosine. And so, and this is where my R is going. So R goes between 0, between 1 plus cosine theta and 0. And theta goes between pi over 2 and pi. I hope you can understand what I'm drawing. This goes from 0 to 1 plus cosine. So I'm drawing this region on top so far, which is in 2 parts. So part of it looks like this part of the cardioid. This part on this side looks like this part of the cardioid. So that's why I've had these 2 integrals. Then this is going to look like this part of the cardioid. Okay, so now, so this is an r dr t theta plus, let's do the other part. So now I'm going to erase this. Okay, so now let's do the other parts. So I've basically done this first part. So this first part here was this first integral. Then this next part here was this next integral. Now let's do, I don't really care which one I do. Let's see, I'm going this angle. So let's do this part of this region here. So now I have this. So I'm going from pi over 2, from pi to pi over 2. So this is from 3 pi over 2. Theta equaling pi to theta equaling 3 pi over 2. Okay, so I'm going to do this part of the region, which is 1 plus cosine is out here. And so this sweeps out the whole little slice. And so this goes from theta equaling pi to 3 pi over 2. By the way, by symmetry, you could actually have just done half of this and then doubled it. But I'm not going to do symmetry, I guess, right now. I'm going to do the whole thing. It's going to be a little of a pain, but okay, so this is a lot of integrals then. Without using symmetry, that's going to be a lot of pain. And so this goes from 0 to 1 plus cosine theta r dr d theta. And then the last one plus. So now let's do this last part here. So this last part. So I'm going from 3 pi over 2 to 2 pi. And then this is a 1 minus cosine. And so if I look here at this and sweep it out, so I just sweep this out, this gives me the integral from 3 pi over 2 to 2 pi. Integral from 0 to 1 minus cosine theta. And this is 1 time, I'm integrating in 1. So this is r dr. Did that answer your question? How I'm figuring out each of these limits of integration. Yeah, okay, good. Okay. So now we're gonna integrate. So this is equal to integral from 0 to pi over 2. Integrate this guy, so that's 1/2 r squared. Between r equaling 0, r equaling 1 minus cosine theta, d theta. Plus, it's the same thing. Integral from 0 from pi over 2 to pi of 1/2 r squared. Between r equaling 0, r equaling 1 plus cosine theta, d theta, plus 3 pi over 2 to pi 1/2 r squared. I need more room. 1/2 r squared. Mean r equals 0. R equal 1 plus cosine theta. Lastly, integral 3 pi over 2 to 2 pi 1/2 r squared between r equals 0, r equal 1 minus cosine theta. Okay, so this is equal to integral 0 to pi over 2, 1/2, 1 minus cosine theta squared. Minus, plug in 0, you get 0, d theta. plus integral pi over 2 to pi so it's 1/2 1 plus cosine of theta squared minus 0 plus integral 0 to pi over 2 of 1/2 1 plus cosine squared. So let's actually do that. 1 plus 2 cosine theta plus cosine squared theta plus integral. Oh, why did I say 0 to pi over 2? Don't know. That's, I'm looking at the wrong thing. 3 pi over 2, pi to 3 pi over 2. That was definitely an error. Okay. Okay, looked at the wrong line. And that's 1 plus cosine. And then 3 pi over 2 to 2 pi to 2 pi. And this will give you a 1/2 1 minus 2 cosine theta plus cosine squared theta d theta. Okay. Obviously, these are the same. These are the same and those are the same. So let me add another page here. So this is equal to integral 0 to pi over 2, 1/2 1 plus 2 cosine theta plus that's a minus. That's a minus there, didn't I? That was a minus in the first one. Plus, well, just recall that cosine squared theta is 1/2 1 plus cosine 2 theta. The half angle or double angle formula, which whatever that. Okay. So this is 1/2 cosine 2 theta d theta. Will I be able to? I'm going to have to just write this as 4 integrals on 4 lines because I don't have enough room. Pi. Of course, these I can write together because these are both pluses. So these two are both pluses, and it really goes from pi over 2 to 3 pi over 2. One half, and the only difference is a plus sign. And then the last one is the same as the first. Plus integral from 3 pi over 2 to 2 pi of 1/2. So those are minuses. 1 minus 2 cosine plus 1/2 cosine 2 theta. Okay, so let's integrate. So integral, so it's 1/2. Integral is theta. Derivative of sine, so that's a minus 2 sine theta. Plus 1/4 sine two theta for theta between 0 and pi over 2. And then the same thing for the next line. Plus, change that to a plus, and that's pi over 2 to 3 pi over 2. Plus the same thing. Except it's 3 pi over 2 to 2 pi equals. Okay, they're just all the same integrations. So I was lazy and I just plugged them in. Okay, so this is equal to where's the 1? Where's the 1? 1 plus a half gives you 3 halves. So that was a definite typo there. That should be 3 halves. Because I have a 1/2 times 1 gives me additional 1/2, which I should have added to the 1. So that should have been a 3 halves. So these all have to be 3 halves in front of this, or I'm going to get the wrong answer. Sorry about that. That was definitely a typo there. I just saw good. I saw it at the very end. Okay, sorry about that. This is pi over 2. I'm going to only do the first line. Okay, so that's 3 halves times pi over 2. Okay, minus 2 times sine of pi over 2 is 1. Sine of pi is 0. Plug in 0, you get 0. Plus 1/2. 3 pi over 2. Okay, so that's 3 halves times 3 pi over 2. Okay. Okay. Sine of 3 pi over 2 is a minus 1. Sine of 3 pi is 0. Pi over 2, so minus. Plug in pi over 2, so that's 3 halves. Pi over 2. Plug in pi over 2, so that's 1. So I'm subtracting. Okay. Plug in pi over 2, that's 0. Okay. Plus 1/2. That is 3 halves times 2 pi. Sine of 2 pi is 0. Sine of 4 pi is 0. Minus 3 halves times 3 pi over 2. Sine is minus plus, but I'm subtracting, it's a lower limit. It's a minus 1. Sine of 3 pi is 0. Let's see if I get this correct now. Okay, so this is equal to, that's 1. Oh. I should have written that as a 2. So that's goes with this. And I have a 3 over 2, a 3 pi over 2, which cancels with this one. And so I finally have, well, 1/2 times 3/2 gives you 3/4 times 2 gives you 3/2 pi. I have 2, 4, 6, 8 divided by 2, which is 4, so I have -4. And that is your answer. Let me do problem number 20. Use polar coordinates to find the volume of the given solid. So we have some cone, and we want to do this above some ring. Okay, so don't know if I can draw this. Let's see if I can draw it. Okay, so you have oh, that's not too bad. Okay, and let's see if I can draw this. Okay, so let's see. So this is going to be a 2, and that's going to be a 1. Okay, so, and let's do, so this is X, oops. Y, Z. And so I have here Z equals the square root of X squared plus Y squared. And so I want to figure out this volume. Okay, so it's if I don't know if I'm gonna miss it up once I show the volume. Yeah, that's not too horribly bad. So it's this. Yeah, that actually doesn't look so horribly bad. Okay, so I have this cone here above this region here, this little annulus, this ring, and the radius of this, well, goes between 1 and 2, since x squared plus y squared is r squared. Okay, and so it's going to be just sort of like, I don't know, a cup or something with a hole. It's sort of a cuppish type of thing with a hole in it, but it's a conic. It's a conic sort of part. So this is sort of like a cone, and then this is sort of like a cylinder. So it's a cylinder where you have just a little bit of a cone top part of it, and you want to find the volume of that sort of weird, sort of cuppish type thing. Of course, it doesn't have a bottom, so it's sort of a weird cup because things flow out of it. Okay, so I'm going to integrate this. Oh, so notice that if I use polar coordinates, then x squared plus y squared is just equal to r squared. So in this case, this is just r. And the bottom here, the ring, 1 less than x squared plus y squared, which is less than 4, is the same, r being between 1 and 2. Okay, so let's find the volume. So the volume of this is going to be, well, the theta just goes between 0 and 2 pi, my angle. My radius r, well, my radius goes between 1 and 2. And z, maybe I'll write, well, the z is r, and then I multiply by r, dr, d theta. Because you always multiply by r, dr, d theta. And I'll give 2 differing reasons why it should be r, dr, d theta in the future. And so this is equal to integral from 0 to 2 pi. Oh, maybe I'll just write it as r squared from 1 to 2. R squared dr d theta. So now let me integrate. Integral from 0 to 2 pi. Integral of r squared is, well, 1/3 r cubed between r equaling 1, r equaling 2. So let's integrate, so let's evaluate this. Let's plug in 2. And so it's 1/3, 2 cubed minus 1/3, 1 cubed, d theta. Well, 8 minus 1 is just 7. And so this is just equal to integral from 0 to 2 pi of 7/3. So if I integrate that, I just get 7/3 theta between 0 and 2 pi. And so I plug in, I get 2 pi minus 0 is just 2 pi. And so this is 7 times 2 pi is 14 pi over 3. And that is your volume. And so that finishes off section 13.